Hello friend, welcome back to the TRSDOS channel. I'm Dr. TRSDOS. I was just doing with my spare time what I always do with my spare time, reading Captain Zilog, as I hope all of you do. Captain Zilog comic has a lot to offer for those that are desiring more information about Zilog. I'm not sure where their marketing campaign was going with this back in the day, but they were going somewhere, I guess. Anyway, I wanted to go back to what we were working on, our sample program. I changed the format of the recording software, so I'm hoping that this will display the simulation a little better this time. I left the same program that we left off in the last video. I'm going to do a little editing here to maybe make it a little more readable as we go. As I said before, the development system allows us to edit code and run in the simulator virtually here in the same window. One of the things I like about the development system, it allows blank lines without marking them as comments. With a semicolon the way we traditionally would, and this can make the code a little more readable, having blank lines separating without any characters on the line at all. I feel it adds to the readability a little bit. So before I put the break in a bad spot, I think you're in the no-op or something, and that made it maybe a little difficult to see the value of the registers and as it progresses through this loop. Again, let's go back to the beginning. We have a file called demo.s for source. You can edit that with a notepad, or you can edit it here in the development system. I prefer to use Notepad when we're not, when I'm doing larger development projects. But we can see here that it's storing that on my desktop, a file called demo.s, that's here in this left pane. And here, this is the output pane that they refer to in our view. We have the workspace, which we just had up, the output, which is at the bottom, and the status bar that's in the output, I believe, tabs at the bottom. So we're going to leave the workspace up, we're going to leave the output up, because with this really small project, we have enough room to display them all at the same time. Here in a moment, we're going to bring up the window that shows the UART output and also shows memory and a disassembly and registers, etc. That's why for people even learning assembly language program, this is a great, this development system is great because you can run small programs and stop them and view the registers and understand how the instructions, and even for veteran programmers, you're not really sure how that is going to work, that instruction is going to work in a certain situation. You can set that up here, run it, break it, and examine and see what's happening. So again, to start over, these were assembler directives that set up the title that would go at the top of any listings of this program, and the define statement defining this segment of code I called startup as using RAM space starting at 3000 originating hex. and RAM memory. This is important. We always need assume ADL equals 0. This makes sure you come up in the Z80 mode. Otherwise, you're going to come up in 24-bit addressing. Org 3000 hex. Okay, this is standard with most all assemblers to use that format, that syntax. Hopefully, you've done some assembly language programming. If not, this is your first time. We're telling the assembler to originate and assemble this code as if it's originating at this address in RAM. So we start demo as our first label, which is a comment. I'll do a no-op. I made up some random instructions pretty much, but we will start A off with a 1 in it, the B with 0, which we just in the last video covered that with the decrement and jump non-zero instruction, which decrements the B register and loops if it is not 0. If we start off with 0, since it does the decrement before it does the test, this means that it'll loop 256 times. You just have to take my word for it. You can play with this, and this is where we're going to put our breakpoint, right here. So at the top we can tell the assembler to insert a breakpoint right here. Before I called this a red ball, I think they mean for this to be a red stop sign. It's going to stop right here each time we go through. So this, you may not have been able to see it in the last video, but this is the go. It's going to compile, assemble, and load into the simulator and go. It's wanting to know if we want to rebuild the project because it's changed. We've updated the source code. Now, the output, you can see that it's already running, and on the right we have our UART output. We're not doing any work with the UART. We have our registers, and we have a disassembler showing, and the disassembler shows 300 Bravo, and if we look, that instruction there is our decrement and jump non-zero, and the address back to 3005. So if we look, that is our program that we have here on the left. That is what is in the simulator's memory and running. If we look at we have not executed this instruction yet, so we have not yet executed this instruction. So register B, this is B and C, register B, these 2 bytes right here, 00 are the contents of B, the next one is the content of C. If we were doing 24-bit addressing, that would be so it's 0 because we have not yet done the decrement, then the test. I'm going to go over here and tell it to go. Step. It's already ran this program that quickly. Come back around in the blink of an eye. It's now stopped again at this breakpoint. If we look, the B register at this time has FF. The C register also has FF. Of course, that is because this instruction here, we did transfer the contents of B to C during the loop. So you can see that they'll both change at the same time. I'll go over here in single step. We'll execute the decrement and jump non-zero, which it will. It's already ran that. We look here. Both those registers are now Foxtrot Echo. The accumulator, on the other hand, how we didn't talk about that, but it started off at 1, then it went 2, 4, 8. So let's run the loop again, and it should now double because we're adding A to A, correct? Right here. Each time we go through the loop, we're going to add A's contents to itself, the accumulator. So let's run that. We're going to see, okay, so we get 10. And why does it say 10 and not 16, right? Because this is in hexadecimal. So 10 hex is 16 decimal. If we look at our counters over here, they're down to F Foxtrot Delta, both registers. Both of them should be the same. If I remove this breakpoint by coming here, removing all breakpoints, tell it to go, it's going to run until its entirety and halt until it gets to the halt instruction. Which, if we look, that's exactly where it's at after I told it to go and then break. Our A register has overflowed. You can decode the F register. We'll get into this on another video. But our flags register, I'm sure if we look, we're going to have the carry flag set. Our B and C register is now a 1. The reason for this, we can get into later, but it did decrement and was non-zero. I have to come back and find out why we have a 1 in the C register.
Easy.
And
No.
they should match the same, so I'm going to have to research that. Oh, I know why, because the C has the contents before the decrement took place. Then the decrement took place, and B was 0. It fell through and halted. If it would have went back around the loop, C would have been loaded with the contents of B again, so they would have matched at that point. And we were stopping before the decrement before. This time we've stopped after the decrement, so that's why that C has the contents prior to the decrement instruction, and B has the contents after. So this pretty well, I hope, clears this up a little further. Coming on down below the halt instruction, we end with start demo, which is where we want the program to begin execution. It's important, just like the org instruction is common to almost all assemblers universally. The end statement is also pretty universal, pretty much across all assemblers. And its purpose is to tell the loader not only this is the end of the program, that you're at the end, but to give it the transfer address, so that when the loader loads the program into physical RAM to execute, the last thing it passes is the transfer address, and in this case, is start demo. And we could have code above start demo. We could have code up here, or data below our org statement. But the transfer address, when it loaded to execute, it would execute and begin execution at whatever followed this end statement. My early days in school on PDP-11s, I was putting the end statement. It would assemble, link. It would load in memory, but my program would not run. You could load, type run from the console. It would load the file. I could compile it. I could do everything. And In those days, we had the programmer's front panel on the PDP-11. I could hold it. I could examine memory. My program was in memory. It just wouldn't start. You could manually start it, and it would run. I had someone that was my teacher that told me I was missing the transfer address, and that's an important thing to understand. If you miss this, your program will compile, it'll load, it'll be in memory, it'll do everything. It just won't start because you don't give it the transfer address. Okay, so for our first assembly language example, I hope maybe this cleared up a few things. And again, you can do this whole thing with the Zilog development system, which is free at zilog.com for download. Completely free, and you need no external hardware, nothing to plug in, nothing. It's all just in simulation here. And it'll let you use their new EZ80 chip. Be happy to help you with any questions. Thanks for watching.